All right, so now let me talk about LU decomposition in general. So let me set up some notation. Let xk, right, denote the kth column of A at step k, right? And then I'm going to choose this matrix BK, which again, if you recall, is representing the elementary row operations one uses in Gaussian elimination. So BK is chosen so that the following is true, right? That xk, which is x1k all the way up to x. Okay, so I'm going to sort of actually bring it down to the diagonal entry xkk, then x k plus 1 k, and then finally all the way up to x nk. Right, so this is chosen in such a way that when you apply bk to xk, you get the following: x1k all the way up to xkk, those remain the same, and then everything else is 0. Okay, right, so all the entries below the diagonal of that column get zeroed out by this B matrix acting on it. Okay, so to do this, if you recall, right, what you do is that you take, the Jth equation and you map it to Ej minus Ljk times Ek, where Ljk is just that entry, corresponding to the appropriate row divided by the thing along the diagonal. Right, so that's just xjk divided by xkk. All right, so with that in mind, the matrix BK looks like the following, right? So it's 1s along the diagonal, and then in the kth column, it looks like minus, so this is going to be minus L k plus 1 comma k all the way up to minus L n k. So if we recall, it's like we had this stroke of luck, if you will. That the inverse of this BK inverse is essentially the same matrix, except that this sort of subdiagonal column, right, has the signs changed. So it's a bunch of 1s, and then you have L k plus 1 comma k all the way up down to L n k. And then the other stroke of luck is that when you multiply those matrices together, the inverses of those matrices together, they sort of just all stack together into a nice lower triangular matrix. So stroke of luck 2 is that L, which is B1 inverse up to Bn minus 1 inverse, is going to be, right, this diagonal 1s, this is 0, and this is L21 to Ln1, Ln2 all the way up to Ln n minus 1. Okay. All right. So this gives you that A is equal to L times U, right, where L and U are constructed using elementary row operations. Okay. All right, so that's kind of nice. All right, and the advantage, as I sort of alluded to before, is that by factorizing the matrix A into a product of a lower triangular and upper triangular matrix, after you've done that, which obviously requires some effort. After you've done that, then it becomes very, very easy to solve the equation ax is equal to b for an arbitrary right-hand side. Okay, so let me just stop here for now.